Thanks, Liz.
Yeah, totally. So, okay, I'm hitting go live. So from now, anyone on the YouTube could theoretically
Listen to our conversation.
listen to whatever we're saying. Okay, so let's see if it's
live.
Both live. Okay, and it's at the link we think? Cool. Okay,
Yeah,
perfect.
awesome.
Awesome.
Sorry, Tuhin, we had a hiccup with this last time.
No, that's okay.
But yeah, it should be fine for your talk.
I guess it's almost comforting, we're always going to have technical issues, virtual, in person. There's one constant in this ever-changing world.
No matter how many talks we host. So we typically start like a couple of minutes after the starting time. So just wait.
Okay.
If
No, that's okay. Yeah, it's only 12.
I'm just gonna send out on the email to the mailing list to remind people that it's happening now.
Sure.
Tuhan, I forgot. Did you say that you're okay with questions during the talk, or do you want to save them all for the end?
Yeah, I think in general it's okay if it's like one or two questions. I think like if it's just like too many questions in between, sometimes it like interrupts the flow. So yeah, I mean, I guess like one question would be good, like, because I think I'm gonna talk about like 3 subsections. So like usually it's okay to ask questions after one subsection.
Okay, great. So you have like these pauses and people can just ask them.
Yeah, sure. Yeah.
Sounds good. Awesome. Um, okay, let's start, I guess. Yeah, hi. Welcome everyone to another edition of NLP with Friends. Today we are super happy to have Tuhin, who's an awesome PhD student at Columbia University based in New York and advised by Smaranda Murison. Tuhin's interests are broadly language understanding and generation, especially non-literal language. And let him tell us more about that.
Thanks, Abhilasha. Hi everyone. So as you know, like I got interested in working in figurative language. Primarily one of the reasons being that like figurative language is kind of so common. And I generally am like a big believer in pop culture. So I guess I would definitely talk about this in the beginning of my talk because I feel like there is so much figurative language and pop culture references. Like say for example, like everyone is like, I'm a big fan of Adele, so like say when you heard the song Water Under the Bridge. That's basically an idiom. I'm also a big fan of Amy Winehouse. So like she in her career best single says, in Back to Black says, and life is like a pipe. Or like if you say, take the Simon and Garfunkel song, which says April come she will, May she will stay. So this is basically a personification where Simon and Garfunkel is basically comparing a girl's changing mood to the changing seasons. So these sort of language is very like popular and like widely used in everyday discourse. But even that is the case, like a lot of NLP research focuses mostly on like literal language. So, I mean, in general, figurative language consists of like multiple sorts of like figurative language, say irony, metaphor, simile, personification, idioms, hyperboles, puns, etc. And I mean, I'm sure we all use this like in our day-to-day conversations. I mean, most of the research on figurative language has been on detection. For example, like people have worked a lot on sarcasm detection, people have worked a lot on metaphor detection, and a little work on, say, hyperbole detection or like similes. But these research is mostly on detection. So what are we still missing? Like, I guess we are definitely missing on figurative language generation, figurative language interpretation, and definitely figurative language evaluation. So in the interest of time, I probably will only talk about the first two topics. And these two topics are something which I have worked on during my PhD. So why is figurative language generation challenging and why it hasn't been done till a very long time? So one of the reasons for this is like usually for training a generative model, we would require some sort of like paired parallel data, right? Like, for example, one of the reasons why machine translation was like so popular is because we had parallel data. So for these sort of like, say, I'm trying to like generate sarcasm. So like there is no large parallel corpus of non-sarcastic to sarcastic text to train a generative model, right? So typically because of this, it's really a bottleneck. And let's say like even if there is a large parallel corpus which is present, if you just want to learn the distribution of existing data and sample from it, it is most likely going to mimic or memorize the training data rather than like generating novel or creative text, which is our goal. And finally, one of the very big challenges for these sort of figurative language generation is that it requires a common sense reasoning and world knowledge, right? So if you're saying something like, I love going to the dentist on a Monday morning, the fact that like no one really enjoys going to the dentist on a Monday morning, this sort of common sense or world knowledge should be there. And unless a computer has it, it's really challenging for the computer to then say something like that, right? So when I'm going to be talking about some methods for figurative language generation, and this basically spans across like a couple of work which I have been doing in the last 2 years. The first I'm going to be talking about is generating sarcasm. And this is work published at ACL 2020. And for the interest of time, I'm not going to talk about the generation of simile, but then if anyone is interested, they can definitely read this paper. But I'm going to talk about some work on generating metaphors, which spans across two papers, the Mermaid paper and the metaphor generation with conceptual mappings. So without further delay, let's quickly delve into what it means to generate sarcasm. So like the task which we here are interested in is like that we start from an evaluative non-sarcastic utterance, and we want to generate a sarcastic utterance that keeps the speaker's intended meaning. So let's say there's a non-sarcastic utterance which says, this is a horrible music video. Then our best model generates, this is a great music video. Let's take a look at the ear damage. So as you can understand, one of the reasons why it is sarcastic is because if it's technically a great music video, why would it cause ear damage? There is some sort of like semantic incongruity present, which is often very necessary for creating these sort of sarcasm. So our approach here is that because like getting training data to generate these sort of sarcasm is very hard, so we propose a novel unsupervised approach that are inspired by three main sarcasm factors. One is we want to reverse the valence. We want to retrieve some sort of common sense context. And then once we have done both of them, we want to rank the reversal of valence and the common sense context based on the degree of semantic incongruity between them. And I'm going to just illustrate this in the next few slides through an example so that it becomes a lot more clear. So let's say you have this non-sarcastic utterance input, zero visibility in fog makes driving difficult. Okay, so this is like a literal sentence. So the easiest thing what we can do is just take this input and then just like, let's say, do reversal of valence. So what we're going to do here is we're going to just change difficult to easy. So if you say zero visibility in fog makes driving easy, now you can see that this is some sort of like already trying to be rebellious or some sort of incongruency, because like technically we know that driving in zero visibility is not easy. But is it enough to make a sarcasm really creative, humorous, or engaging? Not really. So like, I mean, this is super easy and you can just do this using a rule-based like thing. So what we say that just reversal of valence is often not enough. So what extra can we do on top of this? So what we do is, how about we retrieve some context related to this sentence, which is compliant with our common sense. So say zero visibility in fog makes driving difficult. And we all know that this is possible because zero visibility in fog causes accident. You can get a ticket, it can cause visibility problem, visibility loss, or like you can say lose your car. So these sort of causality is really important for sarcasm, right? Because every time you try to generate a sarcastic utterance, there is some sort of cause and effect, which is like kind of latent here. And of course, language models are not at that place where they can really understand the causal relationships and kind of generate this fluently. So here we take help of an adaptive knowledge model called Comet. So what Comet does is when you give it a sentence, it produces common sense relations on demand. So like, for example, if you give this input as a sentence, then it gives you these sort of like that it causes accident. So now our hypothesis is, how can you use this common sense to make the sarcasm more creative and engaging? So let's say you have zero visibility in fog makes driving difficult, and then you basically remove the stop words and you feed this to Comet. Then Comet is going to give you the output as accident. So once you have accident as the keyword, what you're going to do is you're going to check a retrieval corpus and see for sentences which basically begin or end with the word accident. So this way you can see that we can get a bunch of like retrieval common sense context. Suffered 3 cracked ribs in the accident. I injured my spine in the riding accident. So you have a bunch of like context which is containing the common sense. So now remember that you have the reversal of valence output as well, which is zero visibility in fog makes driving easy. And then you have this bunch of common sense context. But remember, I talked about semantic incongruity. So a lot of common sense context might not be semantically incongruent to this sentence, right? So ideally, the best sarcasm is one which has like a lot of like incongruity between it, right? So to enable this, what we can do is we want to measure the degree of incongruity between the reversal of valence output and then these common sense context that has been retrieved. But one of the challenges here is, again, that there is no like degree of incongruity classifier, right? Like basically, you would also require some sort of like scores to measure the incongruence between the two sentences. But what we can do is we can rely on a proxy. So let's say like, we know that the multi-NLI data set has like 3 sorts of like labels, like entailment, contradiction, and neutral. So what we can do is we can take say a Roberta large model that is fine-tuned on the multi-NLI data set. And what we can do is every time we take the reversal of valence output and each common sense context and form a pair and feed it to the Roberta large model and get a contradiction score. So what we are basically here doing is using the Roberta model to get contradiction scores for each pair of common sense context and the reversal of valence. And then what we can do is basically we can rank based on the contradiction score. So the one which has the most amount of contradiction score is the one that is most semantically incongruent, right? So with this, we will rank all the common sense context. And finally, the one that has highest level of semantic incongruity with the input, which is zero visibility in fog makes driving easy, we are going to take it and just simply append it to the first part. So then it becomes zero visibility in fog makes driving easy, suffered 3 cracked ribs in the accident. So as you can imagine that this is incongruent and this is also containing some sort of common sense knowledge, and it's at the same time introducing some sort of humorous effect where you know that if it was easy, then why would you suffer 3 cracked ribs in the accident? And it also kind of is naturally flowing because you know immediately that driving in fog is basically causing accident, but you're using it in a funny way to say it because you're basically saying the opposite, but also making it coherent and grammatical. So basically what we did is we started with this input, zero visibility in fog makes driving difficult. And with all our different subcomponents, we finally created the sarcasm, zero visibility in fog makes driving easy, suffered 3 cracked ribs in the accident. So to evaluate this, we have several ablations. So which means that, say, if we are just using the reversal of valence component, like nothing else, just zero visibility in fog makes driving easy. Like, is it enough? Like just using the reversal of valence component. And then say we also have no reversal of valence. Like we basically ignore the first half and just take the common sense context that is retrieved. And then another ablation which we do is no semantic incongruity, which basically means that we randomly select one common sense context from the pool of common sense contexts. We just don't rank them based on the contradiction score. There is also state-of-art model for sarcasm generation, which we compared. And then there was the full model, which I just showed, and then also compared this with like human written sarcasm. So the results are something which you can see here. We evaluated this on 4 metrics. One is creativity, one is sarcasticness, one is humor, and one is grammaticality. So as you can see here, the yellow bar, which is the full model, is basically better compared to like all other ablations or baselines in terms of creativity, sarcasticness, and humor. When it came to grammaticality, we saw the reversal of balance was kind of preferred more. And we posit the reason for this could be because like they are more shorter, right? So like sometimes people think that if there are longer, and because this is also a retrieval-based approach, like sometimes if you just like do a retrieval-based approach, it's not as grammatical as we hope. So it sometimes gets like lower scores from Turkers. So as we show that here, all the 3 components, which means reversal of valence, retrieval of common sense context, and semantic incongruity, like all 3 are really important here to form a complete sarcasm because individual ablation components don't rank up as high to the full model. So so this is a simple like trick through which you can like use an unsupervised approach to create sarcasm without any pair or like label data. And there has been a lot of interest in the community on generating sarcasm. Like after I published this paper, several people have been looking into these sort of like generating sarcasm or like what it means to generate like these sort of things. So I think it's definitely encouraging, and there is a lot of work which can be done in this area because our work was like more a primitive work. But as language models are becoming more fluent, like I have personally tried using GPT-3 to generate sarcasm, but I feel it's really difficult. Like even for GPT-3, probably it'll just generate something like very, very like different, which is not at all sarcastic. So I think this is definitely something which is promising. And like, if someone has any question, I would love to take that. No, I didn't use parallel data. I think that's what I was talking about. Like, because there is no parallel data, this entire approach was an algorithmic unsupervised way to do it because like there is no parallel data of literal to sarcastic. If there was parallel data, then that would make our life a lot more easier. But yeah, I mean, I guess there is no way. So yeah, I mean, if there are more questions, I'm happy to take it. Otherwise, I'll just move to the next part.
Okay, sorry. I wanted to know you used unsupervised method in this approach, but you don't have any test data. How did you evaluate?
I have test data. Yeah, I didn't talk about the test data, but we do have test data. So we evaluate this on like 150 literal sentences which were taken from prior work, and we generate sarcasm based on like our algorithm on that test data. So these are like all of the details are there in the paper. Like for the brevity of time, I didn't go about on the test data, but you can see all the test data in the GitHub link for this paper. So we definitely evaluated it on the test data, and these results you see are the evaluation from the test data.
Okay, great. Thank you so much.
Yeah. Welcome. I guess I'll just move to the next part. So we saw like how we could generate sarcasm. So like, let's take a quick look at can we generate metaphors and like what it means to generate metaphors. So here we're trying to like, given a literal input sentence, generate a corresponding metaphoric sentence. So let's say if you say like the house where love had ended, okay. So like, yeah, I mean, I guess it's a pretty literal sentence. But when you say the house where love had died, it's basically metaphoric, because like how like love is not a person, right? Love cannot be born or love cannot be died. The moment you say something like that, it's basically metaphoric. So it's kind of a tricky task because it's not quite style transfer, but it's also not quite paraphrase generation. So let's say like what basically we are trying to do here is in doing that, like first I'll talk about the mermaid paper, where say you have this corpus where there are a lot of sentences. So for our work, we use the Gutenberg poetry corpus, which would already have a lot of metaphoric sentences in it. So what we would first do is we would identify sentences which contains a metaphoric verb in it. So like, let's say the house where love had died. So you can use a metaphor detection model to already identify that died is a metaphoric verb here. So then what you can do is like, you can use mask language model to basically mask died. And then what you can do is like, you will get a bunch of replacements from the mask language model, right? So this could be love, the house where love had started, or the house where love had ended. So of course, in order to create any sort of parallel data, you just not only need to have replacements, but you also need to like ensure that there is semantic consistency, right? So when someone is saying the house where love had died, so like they are trying to like express a symbol of loneliness, life, loss, despair, or these sort of things, right? Whereas when someone says the house where love had started, it's more trying to like say a positive thing, like life, marriage, romance, passion. So like, I think this, so what we do here is we basically take a comet and get like the symbolic meaning for every sentence, right? So with this, what happens is we have the initial metaphoric sentence, and then we have a bunch of literal replacements from the MLM, where we then compute the overlap in the symbolic meaning between them and honor the one which has most amount of symbolic overlap, right? So as you can see here, the house where love had died has a symbol of loneliness, loss, despair, love, etc. So once we get that, we then take the intersection between the symbolic meaning for all the replacements. And here clearly the house where love had ended comes across as the winner compared to the house where love had died. So this way, what we are doing is we are starting with metaphoric sentences, and then we are creating the literal paraphrases using masked language model and symbolism. So this way, even though we don't have parallel data, what we're eventually doing is we're creating parallel data in a weakly supervised fashion like this. So if you see, like our approach is kind of like this, that the house where love had died, so you basically mask died, and then you basically had the house where love had ended. So the house where love had ended, these part are literal sentences, and the house where love had died are metaphoric sentences. So using this, you can train a sequence to sequence model then to basically generate metaphoric sentences that are conditioned on literal sentences. But one of the challenge also again here is that, I mean, there is no fixed metaphor, right? So the thing is, like, you say like the house where love had ended. So now this can be like said into multiple ways. The house where love had died, the house where love had collapsed, the house where love had floated away, the house where love had bit the bullet, or the house where love had burned down. So like all these things are metaphoric, right? So how do you know basically for one literal input, how can you generate the appropriate metaphor? So one of the things which comes into metaphor is like that it is grounded in this like theory, which is called the conceptual metaphoric theory. So here basically what happens is metaphors are always built from an abstract target domain and a concrete source domain. So if you see this example, argument is war, like this is a mapping. So here if someone says, your claims are indefensible, he attacked every weak point of my argument. His criticisms were right on target. He shot down all of my arguments. So you see like here this like domain mapping argument is what is kind of reflected. So always in conceptual metaphoric theory, there is a target to a source, like A is B, that sort of like mapping. So we basically think that we can also use this sort of a mapping to like generate our metaphors. So in doing that, what we do is basically, we already talked about the literal and the metaphoric sentences and how we can create them. So one thing which we do is we basically tag them using FrameNet. And then what FrameNet is giving us, it is giving us semantic frames respective to the verb. So like if you say the house where love had ended, so it gives you the semantic frame cause to end. Similarly, if you say the house where love had died, it gives you the semantic frame death. So what we can do now is we can use these semantic frames which we obtain as control codes to then generate the metaphor, right? So the reason for using control code is then you can generate different sort of metaphors by just changing the control condition, right? So you're not like, typically in a sequence to sequence model, it's not very controllable, right? Because you can only generate one particular form of metaphor. But here what's happening is, like given a particular target domain, and if you just change the source domain, you can generate different sort of metaphor. So if you see here, like the format of our input is then death, a separated token, the house where love had, and then when you have the verb ended, you also like concatenate it with the target domain. So basically with that sort of an input, it can generate this sort of an output, the house where love had died. And you can train a BART model using control code. So with this way, what you can do is like, you can not only use our parallel data, but you can also additionally tag it with domains, which you can get from FrameNet. And with that, you can do is like, you can generate multiple sorts of metaphor depending on any sort of conceptual mapping you want. So some examples, these are like generated from our model. So I wanted to show this. So like, let's say you have something like that, he resisted the panic of vertigo. So like here, resist is something like self-control, right? From FrameNet. And then say you want a mapping, self-control is quarreling. So like if you give this mapping along with the input sentence, then the output is he disputed the panic of vertigo. So here you can see that the frame of quarreling, which is dispute, is reflected. But at the same time, this is also kind of metaphoric because you don't, if you're saying that he disputed the panic of vertigo, which means that he basically fought the panic of vertigo, but it's saying in a way which kind of reflects the frame of quarreling. So here self-control is quarreling is kind of reflected. Similarly, if you see this example, already the thermometer seems close to 90. So here like seems means giving impression, and you're using the metaphoric mapping, give impression is being located. So once we give this input and this metaphoric mapping, then the output generated is already the thermometer sits close to 90. So we all know that like when it's saying something like thermometer sits close to 90, it's very metaphoric, right? Because thermometer is not a person, it cannot sit. But the fact that when you just read this thing, you can understand that it basically means that the thermometer is kind of pointing to 90. So using these sort of like control codes in terms of like semantic frames, you can also change how a single literal sentence can be changed into metaphoric output. So let's take a look at the results. So we have the literal input sentence and the metaphoric mapping. And then we give this to the model. And then the model basically generates metaphor. So for evaluation, what we have is we have expert evaluators, which are linguists or literary professionals. Because what happens is for these sort of like metaphors, if you just like use crowdsourcing platform like MTurk, the evaluations are not that great. So what we do is we recruit expert evaluators who are linguists or literary professionals, and then we evaluate them on metaphoricity and domain evocation. So metaphoricity means how metaphoric is the output, but at the same time, domain evocation, like whatever domain you're giving is the output basically reflecting that domain, which I just showed you that when it says he disputed the panic of vertigo, so dispute is related to quarreling. So is it basically reflecting that sort of domain? So if both of these are there and successful, then only our metaphor generator is kind of successful. So, and this was done on a scale of 0 to 4. 0 means like not at all metaphoric, and 1 means metaphoric. So as you can see in the results here, so like so what I talked about in this talk is the CM BART model, which is our best model, but there were already prior work. One was done in 2020 by Kevin Stowe. And then like the second bar chart, which you see, Chakrabarty 2021, this is from our mermaid paper, where you don't have any sort of like domain information in terms of control code. So it was just how we created the parallel corpus from literal to metaphoric, and what if we just fine tune BART on top of that. So that model, even though it does like decently well, it's still kind of behind the CM BART model. So the CM BART model, which I just talked about, is actually the most metaphoric model. And what's particularly encouraging and inspiring for us is that in terms of domain evocation, it's the model that is a lot better, because like we especially add control in form of domain information, right? So then it can generate metaphors which are not only metaphoric in terms of their output, but also can basically reflect the like target domain and the source domain in a better way. So yeah, I mean, I guess that's how we kind of generate metaphors. And if anyone has any questions around that, I'll be happy to take it. Someone is connecting to the audio. Feel free to write in chat as well if there is a problem. Yeah, if anyone doesn't have any question, I'll just move to the final segment of the talk. And this is a very recent, someone asked a question. What is the practical application of this? Yeah, I mean, I guess that's an interesting question. One of the practical applications of being able to generate metaphor is definitely you can use this in sort of like a conversational agent. Like say, for example, in educational purpose, you can also use it where like, say you have an application where you're trying to teach kids how to generate metaphors or similes or these kind of things. So you can definitely use these models to like kind of generate and like show this to like kids for education. I know that people in automated essay writing, say for people who are working at educational testing service like GRE or stuff, they work a lot on like metaphors or like understanding metaphors, generating metaphors, or building applications for kids where they can use these sort of things. But in general, one of the points about figurative language generation is also like a lot of these can be used directly in conversational dialogue. So I guess like if you're having a conversation, you can always like, or say like as we place more reliance on writing assistants or creative writing assistants like Grammarly or these sort of things. So if you just want to make your writing more better in terms of like essay writing or something, you have a literal sentence and you can easily change it to make it more fancier or metaphoric. So like, or like say you're writing poetry using like a GPT-2 or something. Like sometimes what happens is like the sentences are very generic. So you can use this as off-the-shelf tool to kind of make your poetry generation models or something like even more better and like metaphoric. So yeah, I mean, I guess you can use it on top of like a lot of applications. Okay, so I'll just like quickly go to the final part of the talk. And this is some work which I did during my internship at AI2. And this talk is about, it's called, it's not rocket science, interpreting figurative language in narratives. So this work is gonna come soon at a nearby conference. It just got accepted to tackle and I'm like working on the final draft. So yeah, I guess this is a super fun project where like idioms are kind of like really difficult for language models. So figurative expressions such as idioms are often non-compositional. For instance, the idiom chicken feed denotes a ridiculously small sum of money instead of food for poultry. So difficult for transformer-based language models that heavily rely on word content. And they have shown like very little evidence of nuanced composition, right? So like if you give chicken feed to a transformer-based LM and get the representation, it'll be very close to something like food for poultry compared to something like a ridiculously small amount of money. And transformer-based language models are even more difficult with figurative language, such as similes, which are often created ad hoc. Like, for example, if you're comparing someone's calmness to a high mountain lake without a wind stirring it. So basically what happens is like when it comes to figurative language, traditional transformer-based language models which are trained on literal language do not perform that well. So the thing is like, how can we test if language models can actually understand such figurative expressions? Like there has been a lot of work on detection, but what happens with detection is like, sometimes there are spurious statistical cues or like some sort of label associations, which doesn't let us really understand if this is actually learning something or this is something totally else. So what we can do here is, what we do is we design story close tests like rock stories, where narrative ends in an idiom/simile. But to choose the story ending, you not only need to understand the story context, but also the figurative expression. And in the rock stories like task, originally it was a discriminative task where you were supposed to choose the correct ending between two options. But we also have an additional task along with the discriminative task, which is generate a plausible ending. So here I want to quickly show two examples. So let's say if someone says, I'll ask you once more, how much did you make by a fighter taking that dive? The boy hesitated. $1,000. Luciano laughed. That's chicken feed. So when someone says something like this is a sort of narrative. So the more plausible hypothesis is, next time you sell your honor and dignity, try to hold out for more. So, and then like the implausible hypothesis, well, I guess you made more for taking a dive than you could have as a fighter. So the thing is, unless you understand the meaning for chicken feed, you basically cannot choose the more plausible hypothesis. Similarly, for the simile, if you see like where someone says, his energy shifts once again. Now he feels like a high mountain lake without a wind stirring it. So here, basically, it's trying to like imply the property of calmness. So the more plausible hypothesis is, he doesn't feel the same as he did. Now he's more calm. The incongruent hypothesis is, he still had this rage pent up inside him. So basically, you can see that unless you understand the meaning of the figurative expression, you cannot choose the correct hypothesis. So here there is an extra additional layer of difficulty where you not only need the understanding of the context, but you also need to understand particularly the figurative expression in order to choose the correct hypothesis. So a model which doesn't understand that will not be able to do it. So we basically, in order to model this task, we rely on like some sort of like understanding on how L2 learners or like people whose native language is not English, they understand idioms. So it has been shown that 57% of the times it comes from the context, and only 22% of the time it comes from literal meaning of the constituent words. So let's say this is a very simple example where someone says, there is a sentence, Robert knew that he was robbing the cradle by dating a 16-year-old girl. So here they were asked to interpret the meaning of robbing the cradle. Like, let's say you just don't understand what this idiom means. Like, how would you infer the meaning of this? So cradle is used to associate the meaning with babies and indirectly with very young age. And along with the context, he is basically inferring that it means that he is dating a very young person. So basically what happens is when you don't know the meaning of the idiom, oftentimes you get the meaning of the idiom either from like the constituent words in the idiom or from the context itself. So using this sort of like idea, we can also model our NLP systems. Especially when it comes for similes, it's a lot more easier compared to idioms because like you can just have the literal property of the vehicle and that will make you understand. So like, let's say if there is a simile, the place was like Antarctica. So the Antarctica has the property of being cold. So basically just by knowing that, you can have an idea about like what the simile is basically trying to say. So as you can see that even for understanding these sort of figurative expressions like idioms or simile, you basically require some sort of external common sense knowledge. So here is a very like neat diagram of like what we are basically doing. So let's say you had the narrative and then you had the final sentence. It was indeed my turn to run the gauntlet. So now let's say you don't know what the meaning of run the gauntlet is, like which is very possible. A lot of L2 learners don't know what this means. So what we do here is we have two separate models. One we call the context model and one we call the literal model. So for the context model, what we will do is say this is the sentence which contains the idiom. If we discard that, then basically there are 4 other sentences. So what we do is we get a lot of common sense inferences from those 4 sentences using the para-comment model, which is a discourse-aware common sense knowledge model. So using this context-based like a common sense model, we can get inferences like the narrator sweats, the narrator is seen as scared, the narrator wants to feel better. So the thing is, like, when you get these sort of common sense inferences, it makes it more plausible for you to guess the meaning of run the gauntlet, which means that you're already scared, you're sweating. So which means that run the gauntlet means just running fast away from some sort of danger. So if just you have inferences from the common sense context, then you can actually guess the meaning of the idiom. So this is the context model. But then also when it comes to the literal model, so you can also get inferences from individual word. So like, let's say here it said that gauntlet is used as a weapon, right? So you can understand that it's some sort of weapon. So like when it says that run the gauntlet, you mean that running away from something which is kind of scary or dangerous. So the fact is, like, in order to understand an idiom whose meaning you don't know, you can have these sort of separate models, which is context or the literal model. And how do we do this? We get all the inferences, and then what we will do is we'll take the inferences and convert them into natural language format, as you can see in the diagram below. So run is used to get exercise, and then there's a separator, which is the entire story. And then there are the continuations, which is like, I took a deep breath, convinced it was time, and ran full speed away from the cliff. And then this is the correct continuation, and the incorrect continuation is ran full speed towards the edge of the cliff. So why would you, so run the gauntlet means running away from the danger. So basically the first is the correct answer. So what we'll do is we'll take the common sense inferences and append this with the narrative and the continuation, and then feed this to a Roberta model. So for every narrative, we will have 12 inferences, because that's what we could fit while training our model. So then for every 12 inferences, the Roberta scorer will give you a score. And then what you're going to do is you're going to sum this up, and then you're going to predict the argmax for every continuation with, and then based on whichever is the higher, you will choose that continuation as the correct answer. So what we are basically doing is we are taking the common sense inferences, and then for separate models, literal and context, we are basically training and seeing that if by integrating knowledge from common sense knowledge models along with the text, we get better results. So this is for a discriminative task. And then for a generative task, we basically do something very similar. So we have the common sense inferences and the narrative. So what we do is we fine tune basically GPT-2XL based on these pairs, like run is used to get exercise, and then the entire narrative. But during decoding, what we say is, like, we can merge different common sense inferences together. So what we do is we take 12 common sense inference along with their narrative, and like you can see the prompt is in this format. And then what we'll do is we'll take these 12 like prompts as a batch and feed this to the GPT-2XL model. What the model does is, like, it will generate 12 logits, right? Because it's an autoregressive model, so it generates token one by one. So at the first time step T, it will generate 12 tokens. So what we are going to do is we are going to sum all these tokens. And then so with this summing, we still get a vocabulary size array, right? Because every logit is a 1 cross vocabulary size array. So for the 12 inferences, we get 12 logits, which is like 12 vocabulary size array. We sum them, and then we take the softmax from there. And then whatever vocabulary index is selected, we take the like respective token from that, and then we append this to the like prompt again, which is how like autoregressive decoder model works. So instead of just honoring a single prompt, here we are taking 12 prompt. And the reason for this is the more amount of common sense you will feed into your generative model, the better it is in terms of like generating more coherent. Because from these common sense knowledge models, you also don't know which common sense knowledge is exactly accurate. But what happens is, if you're summing up multiple logits together, then what happens is, like, say something is very less versus something is very big. So eventually what happens is, when you sum this up, maybe one particular vocabulary index becomes dominant over the others. And that is how you can make sure, like, so basically what happens is, like, there is something called exposure bias in generative models. And that sort of thing you can avoid if you're taking multiple prompts and ensuring that your generative model is not focusing on only one particular common sense. So quickly showing the results, we ran a bunch of like baselines. I'm not going to talk about that, but the knowledge enhanced models, especially the literal model, like was better significantly compared to the supervised model for idioms, which kind of shows that like including common sense knowledge from like literal constituent of words help. And then for simile also we got like very minor improvement, but we didn't get like that much improvement. And what is particularly impressive here is like zero shot GPT-3 or few shot GPT-3 is kind of like pretty bad in this corpus, which means that like these sort of like giant language models are not ideally designed to understand these sort of like data. And for generative, what is more impressive is according to prior theoretical work, like context was more helpful for idioms, like as we saw 57%, and for similes it's the literal model. So as we see that we do two sorts of evaluation. One is absolute evaluation, where we basically just see that if the generated continuation by the model is plausible or implausible. So as you can see that for the context and the literal model, they are a lot more plausible than the baseline GPT-2 XL model. And what's particularly impressive is like for idiom, the context model is more plausible, whereas for the simile, the literal model is more plausible if you see in the absolute column. And we also do a comparative analysis where we are taking all the GPT-3, GPT-2 context and GPT-2 literal model and seeing the one which is the best. So here, even for idiom in comparative, the context model came across as the winner. And then for simile, the literal model came across as winner. So this is kind of in accordance with prior theoretical work that context helps more in inferring the meaning of the idiom, but literal meaning helps more in terms of like inferring the meaning of the simile. And this is my final slide where I just want to show like some generations from our model. So like, let's say this is very impressive where like it says like $1,000, lucky Luciano laughed. That's chicken feed. So GPT-2 says he was lucky he made so little, which doesn't make any sense, right? Because they didn't even acknowledge the meaning of the like idiom. But our best model, which is the context model, says Lucky Luciano made much more money by doing other things such as fixing cars or selling drugs. So because he made more money, it's kind of condescending that he's making fun of the other person because like he's saying that's chicken feed. And similarly for the simile, it says like she said her monotone voice and echo of his sister, she was like a high definition TV. So GPT-2 says it was hard to tell what she was thinking, which doesn't really make any sense because here it's not particularly relevant. But our literal model says her voice was so smooth you could hear every word she said, which is more in compliance with the high definition TV, which you can understand is a very unusual simile because usually people don't say something like she was like a high definition TV, but it's basically trying to say that her voice is very clear because high definition TV has that sort of property, right? So Comet tells you that. So this eventually helps the downstream performance of the models. So yeah, with that, I'm happy to take, if anyone has any question.
I'm just clapping on the behalf of everyone in this chat.
Thank you.
Yeah, so great talk. I really enjoyed it personally. If people want to ask questions anonymously, they can ask it on Dory and I'll read it out. But since we're such a small group today also, just feel free to unmute and ask. I have a bunch of questions, but out of courtesy, I
definitely, yeah.
Okay. Oh.
Yeah, just go ahead.
Yeah, so my question, okay, super open-ended question about the first.
Yeah, definitely. Yeah, sure.
Do you have any thoughts about how to do like multimedia sarcasm generation? I guess I was thinking about the "This is fine" meme, which is my all-time favorite meme.
Yeah. You know, I mean, yeah, I guess I mean, there have been some people who have done multimodal sarcasm explanation or like a multimodal sarcasm understanding. Like there is some work, there is a data set also for multimodal sarcasm called Mustard, which basically tries to like generate, which basically annotates using video from like, I think, what is it called? Like the Sheldon Cooper's, like the Big Bang Theory. Yeah. So it takes a lot of videos from Big Bang Theory and then basically like annotates that as like sarcasm. So like, I mean, definitely it's totally possible. I mean, I guess I haven't played with it, but maybe like Clip or these sort of models, VQGAN, they might be already pretty good at like generating sarcasm. But I think like if they are still not there, then maybe like something something like, yeah, I mean, I guess here also common sense could be helpful, right? Say if you're trying to generate a sarcasm for like driving in zero visibility is difficult, like say accident. So like if you prompt the VQGAN or the Clip model by saying that like show someone who has met an accident but he's happy, like, so something like that sort of thing. So like it's mostly how you would design that sort of prompt. But eventually you see the latent theory that like you need to know the causality is like, because I think that's a meme that would make you smile, right? Because like it would show that the person is kind of in a deathbed or like with plasters or something, but then it's still smiling or showing a thumbs up, that sort of thing. So I think, yeah, I mean, it's definitely very interesting. I personally am sort of a noob when it comes to like vision sort of thing. So I haven't looked into this, but I'll be super excited to read like some work which tries to like does multimodal sarcasm. I definitely know people who have done visual metaphors. It's funny because like after I published the simile paper, Devi Parekh did something like that using like I think Clip, where she was trying to like do these sort of like compositional drawing where like a tree like blood vessels. So with this, or like a sun which is shaped like a avocado, something like this. So with this, what happens is like how are these like models like Clip or VQGAN compositional in terms of like trying to compose different concepts. So yeah, I mean, I guess there are a lot of like people who are interested in this field.
That's very cool.
Yeah.
I guess I have one more question.
Sure.
So you mentioned that a lot of the generations, when you were trying to generate sarcasm, had this property that they would have to have some kind of semantic incongruity and they would have to flip the balance of something that came.
Yeah.
So sometimes in sarcasm, like when people go like, "Oh, I am so happy," like when they stretch out SOO in text, you know that it's sarcastic. But that has like,
Rhetorical exaggerations. Yeah.
yeah, that
Yeah,
I
I mean,
guess
I
has
guess.
neither of these properties. So I was wondering.
No, I mean, I definitely agree with you. And I think like when you say that sort of rhetorical exaggeration, I think it comes mostly from speech, because I think sarcasm is very different when written in text versus when said in person. I think like when people kind of talk in a humorous manner, they'll say things like, yeah, it's like, I'm so happy that I am having to go to a dentist. So like something like this. So I think it's mostly like interpretation of how we speak in text. But yeah, I mean, I guess these sort of markers are also very good indicators of sarcasm. But I mean that's not particularly very interesting, because like you could definitely have like a rule-based thing, like where you say that where anything which is like sort of a modifier, you can just like make it a lot more exaggerated, like just through that. So I think like, yeah, I mean, I guess that's definitely a marker of sarcasm. And like, or like using multiple exclamation marks, or
Right.
or like emoji like that. Yeah, I mean, I guess Twitter for form of sarcasm that's really popular, right? So yeah, I mean, I guess like we definitely, and a lot of people have that sort of thing and use it for detection. Like in sarcasm detection, that has been used as a feature forever, like emojis or punctuations. But I mean, I guess like that's not necessary and sufficient. So I guess like in terms of generation, you can definitely use that. But I guess like eventually it's also like to make it more humorous, you would require, I think whenever there is some sort of incongruity, it immediately makes it like funny. So I think like
Yeah.
that's something which we wanted to incorporate.
Oh, that's interesting. So what do you see as like the overall goal of sarcasm generation? Like, why
Yeah, I
should it
think
be
like,
funny?
yeah. I think in general, as you make like, so one of the things is like, also for artificial intelligence, like there is this goal of strong AI where like basically, um so like creating humor is really, really difficult, right? For like AI. So I guess like I think of sarcasm as a very like similar goal for humor, because like sarcasm is basically a part of irony. And even though sarcasm is always tried to be mean, but like verbal irony is not necessarily mean. So I guess like, so you can definitely use this for humor generation, or like say for example like hyperbole in text, or like in terms of like conversational assistance, or like say when you're talking to someone. I mean, I think it can definitely invoke creativity, or like say currently like GPT-3 or these sort of models are like so successful, but then when it comes to like say, it basically cannot generate any sort of humor. So I think like you can definitely use these sort of models to kind of at least like say in a conversational dialogue where like someone is saying that, oh it's raining outside, you shouldn't probably go drive. So like you can give a response which is very bland, or you can give this sarcastic response. So I think like you can say that someone might get offended about it, but I mean there are also benefits that it makes a conversation a lot more engaging. Like it's just like a lot more funnier, right? So I think it definitely depends upon the moderation, like who wants it, or like not everywhere you would like say if you're installing an Alexa at your home, you probably wouldn't want your Alexa to be sarcastic at you. But I think like if there is a use case where someone really wants to generate humor, or like one-liners or puns, like there is a big field of research on generating puns, right? Which is like yeah, I mean recently I've been like also reviewing papers where like people are trying to generate stand-up comedy sort of humor, and like I think it's very, very ambitious. But I mean it seems like everyone is trying to like use these models to kind of try to automate, like, because I guess these are very difficult to generate, because even with few short examples, like you can give me 10 examples of humor, but generating a new humor every time is very difficult. So I think, yeah, I mean, that's probably one of the goals of AI, to just probably be very good at figurative language, because I think like, say for poetry generation, there is like 10,000 of paper which tries to generate poetry, but none of them have won the Dartmouth poetry Turing test, because like ideally the goal is probably AI to write such sort of a poetry which cannot be understood by humans or like differentiate. I mean, GPT-3 is great at poetry, but then it's hard to understand if it probably knows it from like pre-training or something, or it actually has that sort of power.
Yeah, that's excellent. Does anyone else have any questions? I can keep going because I still have more questions. Okay, I'm just gonna ask my host privilege.
Yeah.
Yeah, so that's really interesting. So then I'm curious about what you think about like agents doing some of these more creative tasks, and how that will eventually, like, what role will that play in society? Like you mentioned,
Yeah.
poetry generation and stand-up generation.
Yeah. No. I mean, I guess no. I mean, I think that question also comes up to be like how reliant we are on these sort of agents, right? Because say like recently someone came up to me, pitching an idea about like creating a conversational assistant for like assisted living homes where people are lonely. I think like say for that sort of a thing where you're placing a lot of reliance on these agents, like say you can have a bad day and you can say like, oh Alexa, tell me a joke. So like I mean, I guess like if it can say something like that, or like yeah, I mean in general, or like Alexa say something funny. So I mean definitely it's a lot more harder to be open-ended and funny without any context. But I think like, I mean, these are all like properties which ideally a AI should have, right? I mean, I guess just what is the entire goal of being able to generate like text? Like if you're generating text, you should be able to generate all sort of like things, right? And especially, I don't know if you read this paper. I think Harsh Jhamtani and Varun Gangal have a paper at EMNLP on figurative language in like dialogues, and how models which just like literal language models are very bad, because like sometimes we say that their love was built on sand or something, like idioms or these sort of things, in like, because people constantly use. Yesterday I was watching a show on Apple TV and someone says any port in the storm, and I was like, oh, I now know this meaning because I worked on idioms. But I guess like sometimes like people just don't understand these things, right? So I think like it's definitely important for computers to be able to understand these sort of figurative language and also be able to communicate in it. one thing which is very overarching goal of my dissertation is being able to have this sort of a like human model in the loop kind of writing, where like uh, a, someone can use a creative writing assistant to make their writing better. Like these sort of models can definitely never replace human creativity, but I think these sort of models can definitely make human creativity a lot more better, especially now with like instruction based learning. Like you saw the big science paper, right, where like, so if you just say write a metaphor about pain, so something like that. So like say you're trying to write something and you just want to make it a lot more evocative, so like you just ask a language model, write a metaphor about pain. Now say they supposedly they made a metaphor about pain, so but then you want to use pain in a happy way, so then you say write a happy metaphor about pain. Or say you want to add more constraints, so you say write a metaphor about pain that ends in X, so something like more, even more compositional. So I think there is a lot of scope in terms of like writing assistance, like especially as we place more reliance on these language model based things. Because I mean, a traditional sequence to sequence tuning is good, but it's not very helpful in the long run. But if you can use these sort of like instruction based things to just write metaphors, poetry, or like that sort of thing, like it's really helpful.
Yeah, that's an excellent answer. I really like that vision. Yeah,
Yeah.
are there any more questions in the chat? We're nearing the end of this talk, so maybe one more question.
This is very open-ended, but
Yeah,
it
sure.
seems like one of the hardest things to do here might be to evaluate these things. So do you have any sense, like maybe in doing more generation and getting human evaluations, might there be a way that you could automatically assess them in the future, or what do you see in that space?
Yeah, I mean, that's something which honestly I'm struggling with as well. I mean, I wish if I could just write a paper on evaluation of like these sort of figurative language, I would just like graduate the next day, because it's really hard to like automatic metrics don't correlate at all. Like you can use things like bird score, blue, like they're not that good. And I think like for creative text, it's even more hard because every creative text is very different, right? Humor will have very different sort of like, and then when you're evaluating, there is always, I mean, reference-less metrics are very low, right? So you always need a reference. Now, the point is like for humor or sarcasm or metaphor, there is no one single reference that is correct, right? There can be multiple references, which I just showed that if you're saying that write a metaphor about pain, so like you can write a different metaphor about pain, I can write a different metaphor about pain. So like everyone can write different sort of things. So then how do you ensure uh, yeah, I think it's definitely very, very challenging. Like just to like open domain generation itself, evaluation is like a monster. It's like, it's really difficult. Yeah.
Yeah, definitely. Well, I guess I'm glad that everyone is equally as overwhelmed as I might be with how to
Yeah. No, you are
evaluation,
not alone in this. I guess like we all are. Like the day we have a solution to this, like we'll be all set. Yeah,
but
open-ended. In general, generation evaluation metrics for text itself is like such a big area of research. Like they have the new GEM workshop now for it, because it's just several papers have shown that like automatic evaluation metrics are basically not good. Like they just don't correlate. Like summarization and translation are not the only generation tasks that matter. So
very good point.
yeah.
Cool. Well, yeah, thank you. This is really interesting.
Thank you.
Okay, thanks Tuhin for coming and talking with us about figurative language, and
Yeah, you're
thanks
welcome.
everyone else also
Thanks
for
everyone.
attending.
If you have any
Yeah.
questions, feel free to email me. Yeah. Bye.
Okay. Bye. See you in 2 weeks for Boaz's talk.
Yeah, sure.